So, welcome to our course on fundamentals of transport processes 2. We are now at lecture number 21, just about halfway through the course. And just to recap, we had started off with integral theorems for vector calculus and differential operators. Using these integral theorems and differential operators, we had derived the mass, momentum and energy, mass and momentum conservation equations for a Newtonian fluid, where the stress is a linear function of the rate of deformation tensor. And then we had these were the Navier-Stokes equations for one scalar equation, divergence of velocity is equal to 0 for mass conservation for an incompressible fluid, where the density is a constant, and 3 momentum conservation equations for the 3 components of the velocity, and these have to be solved for the velocity field, a vector with 3 components, as well as the pressure. So, that is where we were. We had then scaled the momentum conservation equation and found that the ratio of the inertial and the viscous terms is the Reynolds number. The equations themselves are nonlinear equations, so it is difficult to obtain a general solution. In fact, this is something that is common to all of transport processes. The equations can be posed mathematically, the boundary conditions can be posed mathematically. However, there does not exist a general mathematical solution procedure which will work for all problems. The solution procedure inherently involves a physical understanding of the physical situation and simplifications based upon those in order to obtain solutions which are specific to well defined limits. Of course, one could solve these equations numerically on a computer using various procedures. However, this does not give us a physical understanding, and the objective in this course was to develop a physical understanding of the fundamental forces that influence the fluid flow in well defined parameter regimes. So, we had first looked at the limit of low Reynolds number, where the inertial terms in the conservation equation are neglected, and the conservation equation just has the pressure and the viscous terms. So, the conservation equations were the divergence of velocity del dot u is equal to 0 minus grad p plus mu del square u is equal to 0. Limit of small Reynolds number, inertial forces are small compared to viscous forces. Alternatively, convective transport of momentum is small compared to diffusive transport of momentum. Therefore, the flow is dominated by diffusion. In the case of heat and mass transfer, when the flow was diffusion dominated, we found that the concentration or the temperature equations satisfy temperature fields satisfy the Laplace equation. In this case, for these Stokes equations, the solution can still be reduced to 2 Laplace equations. Okay. The first is del square p is equal to 0. This is obtained just by taking the divergence of the momentum conservation equation and using the fact that the divergence of velocity is equal to 0. And the second equation was for the general part of the velocity field. And the total velocity field consists of the general solution u general plus 1 over 2 mu p times x vector, okay, where x vector is the vector and p is a scalar. Okay. So, we had seen how to obtain these. So, the solution procedure reduced to solving two Laplace equations, one for a scalar and one for a vector. And we had seen how to obtain scalar, vector, tensor and higher order solutions for these Laplace equations. It started off with the fundamental solution for a point source. We have done that earlier. Del square T is equal to 0, a point source at the origin. The temperature is equal to Q by 4 pi k times the radius, where r is the distance from the origin. Okay. So, if I have a coordinate system, with a point source at the origin, this is an axisymmetric coordinate system. You know that if that point source, the amount of heat coming out per unit time is Q, the amount of heat, total amount of heat coming out per unit time is Q. We have to solve del square T is equal to 0 in the absence of convection around this point source. The solution for that is equal to T is equal to Q by 4 pi k r plus the temperature far from the point source. Okay. So, therefore, the fundamental solution of the Laplace equation for this case is equal to 1 over r, a constant divided by r, but of course, we are specifying these solutions only to within a multiplicative constant. Okay. I can take repeated gradients of this, because if phi naught is a solution of Laplace equation, phi naught is equal, del square of phi naught is equal to 0 everywhere. If I take the gradient of this equation, I find that the del square Laplacian of the gradient of phi naught is also a solution. Therefore, the gradient of phi naught is also a solution of the Laplace equation. That is a vector solution, because when I take the gradient of the scalar, I get a vector. Okay. That is phi 1 I is equal to x I by r cubed. Once again, to within a multiplicative constant. Okay. I can take another gradient and get phi 2 I j. A second order tensor is equal to delta I j by r cubed minus 3 x I x j by r power 5. Okay. And so on. One can take repeated gradients to get higher and higher order tensors. Obviously, okay, these are decaying solutions. They decrease, the value of the solution decreases as r increases, as the distance from the origin increases. Phi naught decreases as 1 over r, phi 1 as 1 over r square, phi 2 as 1 over r cubed, and so on. Corresponding to these, there are also what are called growing solutions. These solutions increase as r increases. Okay. So, phi, the growing solution, leading order is just a constant. Okay. To within a constant is just equal to 1. Okay. That corresponds to this T infinity solution, okay, in my solution for the temperature field, a constant. Of course, if you take del square of this, you do get 0. Okay. Phi 1 is obtained by taking phi 1 for the decaying solution and multiplying it by r power 2n plus 1, okay, or r cubed. Okay. So, the growing solution phi 1 corresponds to I is equal to x I, okay, and one can get the next higher solution phi 2 I j is equal to delta I j r square minus 3 x I x j, okay, and so on, and you will get higher and higher solutions. So, any solution for the pressure or the general part of the velocity field that satisfies the Laplace equation can be written as a linear combination of these, either decaying or growing harmonics. If we were solving for an external flow outside of an object, then we have to use the decaying solutions, because we require that the velocity has to go to 0 far away. Okay. On the other hand, for internal flows, okay, inside an object, we have to use the growing solutions, because the growing solutions are finite at r is equal to 0, which is within the domain, whereas the decaying solutions are not, they diverge as at r is equal to 0. So, based upon this, we had obtained solutions for flow past a sphere, for example. Okay, flow past a sphere moving with a constant velocity u. And of course, the solution for the velocity and the pressure fields, or the general part of the velocity and the pressure, have to be linear in one of the harmonics. They also have to be linear in the velocity of the sphere, okay, because the Stokes flow, as I said, are linear equations for the fluid velocity and the pressure fields. The stress is linear in the pressure and the fluid velocity fields, okay, and therefore, the solutions at every point have to be linear in the fluid velocity and the pressure fields. Okay. Just based upon these simple considerations and the requirement that the fluid velocity has got to be equal to the particle velocity at the surface of the sphere, we had actually calculated the velocity field, okay, 3 r by 4 uj into delta ij by r plus xi xj by r cubed plus r cubed uj by 4 delta ij by r cubed minus 3 xi xj by r power 5. And the pressure was 3 by 2 mu r uj xj by r cubed. We had calculated this in great detail, and from that we had calculated the net force exerted by the fluid on the sphere, okay, which was in the direction of minus u. The net force exerted by the sphere on the fluid is given by 6 by mu r ui. Note that there are two terms here, one which decays proportional to 1 over r as r goes to infinity, and the other which decays proportional to 1 over r cubed. So, obviously, if you are sufficiently far from the sphere, if your position vector is large compared to the radius of the sphere, the only contribution that you will see is the one due to 1 over r, because the one proportional to 1 over r cubed is much smaller. Now, this contribution due to 1 over proportional to 1 over r is like a source term, because we saw for the temperature the heat source, the temperature goes as 1 over r. Similarly, for a source of momentum, that is a point force, the velocity goes as 1 over r. Okay. And the velocity can be expressed instead of using the velocity of the sphere itself. Okay. Instead of using the velocity of the sphere itself, I can express it using the force exerted by the sphere, because the two are dependent on each other. And if I do that, I get ui is equal to pi fj by 8 mu let me write this in terms of the force. One by 8 pi mu delta ij by r plus xi xj by r cubed plus r square by 24 pi mu into delta ij by r cubed plus minus xj by r power 5. Okay, so, this gives me the velocity field in terms of the force exerted by the particle on the fluid. Okay. If we take the point particle limit, that is capital R is small compared to small r, which is the distance from the center of the sphere, this second term goes to 0, okay, because in the point particle limit you are taking small r is very much larger than capital R. In that case, this term actually goes to 0, okay, and you get this is equal to j I j f j, where Jij is equal to 1 by 8 pi mu delta ij by r plus xi xj by r cubed. So, this is for a point source, a delta function in the limit as the radius of the particle goes to 0, but the net force exerted by the particle is still finite, okay, even as the radius of the particle goes to 0. Okay. And this limit, of course, the pressure also follows the relation P is equal to K I F I, where the Oseen tensor for the pressure 1 by 4 pi xj by r cubed. Okay, I should put I here. Okay, so that gives me the expression for the pressure. All of these we discussed, and this is just a review. Okay. So, that is for a particle that is translating. Okay. Just very quickly, for a particle in a shear flow. Okay. Okay. Let's have a particle which is in a fluid in which I have imposed a linear, an extensional flow, okay, far away from the particle. Okay. I have imposed an extensional flow far away from the particle. Okay. So, very far from the particle, I have basically an extensional flow. Particle is sitting at the center. That is always possible, because even if the particle is moving and rotating, I can decompose the flow locally into a steady translation with the velocity at the center of the particle, plus a deformation about that center. That deformation about that center can have two components: the symmetric traceless part of the rate of deformation tensor locally, which gives me the extensional flow, antisymmetric part which gives me the rotational flow. And due to linearity, I can add up the contributions due to each one of these, solve them separately, and add up the velocity contributions due to each of these. Okay. So, for the extensional part, I have already subtracted out the velocity with which the sphere is moving, so that I am in a reference frame moving with the same velocity as the particle, and I look around me and see what is the rate of deformation tensor relative to the particle center. Okay. As r goes to infinity, far away from the sphere, the velocity is just an extensional flow. Okay. Okay. And at r is equal to 0, of course, if you subtracted out the rotation, that means that the sphere is stationary. Okay. So, at r is equal to capital R, ui is equal to 0. Once again, we had solved this problem. Okay. Ui is equal to Eij xj into 1 minus r power 5 by r power 5 plus 5 by 2 Ejk xi xj xk into r power 5 by r power 7 minus r cubed. Okay, so, that was the velocity field. Net force in this case is identically equal to 0. Just by symmetry, there cannot be a force exerted in any particular direction, because there is no relative velocity of the sphere with respect to the fluid. Okay. That we already solved separately earlier. Okay. However, there is a net force moment. Okay. So, if the net force moment, okay, is given by, okay, I will call it as the symmetric part of the force moment Fs Ij, okay, is equal to half integral over the surface of the particle ds of Fi times xj plus Fj times xi. Okay. This is a symmetric force moment, okay, which is equal to half integral over the surface ds of the force per unit area acting on the surface is just the stress dotted with the unit normal, tau I L x L, I am sorry, N L x j plus tau j L N L x I. Okay. If you recall, in the last lecture, on our way to calculating the effective viscosity of a suspension, we had actually calculated one of these. Okay. So, this integral that we had, integral ds tau I L n L x j, calculated over the surface of the particle. We had actually calculated this to get 20 by 3 pi r cubed mu times E I j. Okay, we had calculated this on the way to calculating the effective viscosity of a suspension. So, this is the symmetric part of the force moment. Okay. So, I calculated one part here. Okay. I have calculated only one part here. However, this result itself is symmetric, because this result is proportional to E I j, which was the symmetric traceless part of the rate of deformation tensor. Okay. Therefore, the transpose of this, which is the second part, is also equal to the same thing, because the result itself is symmetric. So, the transpose is equal to the same thing, and therefore, the symmetric part of the force moment is equal to 20 by 3 pi r cube mu E I j. So, the force is equal to 0, but the force times the displacement, second order tensor, integrated over the surface, symmetric part of that is not equal to 0, it is proportional to E I j, and we had used this to calculate the effective viscosity of a suspension. Okay. However, one can do the same thing once again here. Okay. If you recall, when we did the translation of a sphere in a fluid, we had first found out the velocity field in terms of the velocity of the sphere, the force in terms of the velocity of the sphere, and then substituted the force instead of the velocity to find the fluid velocity in terms of the force exerted by the sphere. So, we can do the same thing here. We can find out this velocity, okay, rather than using the symmetric rate of deformation tensor here. I can use this force moment to express my velocity. Okay. And if I do that, I will get a velocity of the form. Okay. It is just simple algebra. I use this relation to substitute E in terms of the symmetric part of the force moment. Okay. And I will get the velocity field as E I j x j minus 3 S I j x j r square by 20 pi mu r power 5, okay, plus 3 x I x j x k s. I'm sorry, I should replace this by this. This is the symmetric force moment. Okay. This is also the symmetric force moment. Okay. Mu all I have done is replaced S, I am sorry, E I j by the symmetric force moment. Okay. And now, if you look at this equation, the term that is the slowest decaying is actually the one that goes proportional to x I x j x k times 1 over r to the 5, because that decreases as 1 over r square as r goes to infinity. Okay. The other two terms decreases as 1 over r to the 4th power as r goes to infinity. Okay. So, in that sense, if I just retain that term alone, I will get E I j x j minus 3 f symmetric j k x I x j x k by 8 pi mu r to the 5th. If I just retain the term that decays the slowest, because as r goes to infinity, this term is much larger than the term that decays as 1 over r to the 4th. And when I have done it this way, you can see once again the velocity field depends only upon the force moment, it does not depend upon the radius of the sphere. Okay. In particular, if I take this expression, okay, if I take this expression, take the limit capital R going to 0, the point particle limit, okay, what I will end up is with an expression like this, because the terms that are proportional to capital R square, okay, will end up going to 0, and I will just be left with this one. So, in the limit as capital R goes to 0, point particle limit, but with the symmetric force moment still finite, okay, I will end up with this result. So, this is the solution for the velocity field for a symmetric point dipole, okay, a symmetric force moment, okay, in which the force moment is basically given by this on the surface. So, that is the response to a linear, okay, shear flow, an extensional flow, symmetric traceless part of the rate of deformation tensor. Okay. So, basically this solution for an extensional flow far away gives me the disturbance to the velocity field due to a symmetric force moment plus an additional term which decreases when you go to the point particle limit. The other thing, the antisymmetric force moment is basically the response to a rotational flow. Okay. So, for example, we found out that for a particle that is rotating, okay, with angular velocity omega, okay, so that ui is equal to epsilon I j k omega j x k at r is equal to capital R. Okay. We had solved this once again, and we obtained the velocity field as ui is equal to epsilon I j k omega j x k r cubed by r cubed, okay. And the angular the torque was equal to 8 pi mu r cubed omega I. Okay, so, that was the torque that I obtained. Once again I can replace, okay, the torque, as you recall, was equal to epsilon I j k integral of the surface ds of x j times f k, okay, acting at the surface, okay, where x j was the position vector to the surface and f k was tau k L and L, okay, the stress acting on the surface. Okay. So, since this epsilon I j k is an antisymmetric tensor, okay, I can also write this as, okay, epsilon I j k is antisymmetric in the indices j and k. Okay. Therefore, this antisymmetric tensor multiplied by this tensor x j times f k, okay, second order tensor x j times f k has a symmetric and an antisymmetric part. The symmetric part multiplied by epsilon I j k is identically equal to 0, because a symmetric times an antisymmetric tensor is equal to 0. Okay. So, therefore, this can also be written as this times the antisymmetric part of this tensor, okay, x j f k minus x k f j. Okay. To get the antisymmetric part of the tensor, you take the tensor, subtract out its transpose and divide by 2, okay, to get the antisymmetric part. So, this is equal to epsilon I j k times the antisymmetric force moment, okay, where the antisymmetric force moment is basically this one. So, I can write the velocity field in terms of this antisymmetric force moment as well. Okay. So, the velocity field expressed in terms of the torque, okay, the velocity field expressed in terms of the torque, okay, ui is equal to epsilon I j k omega j x k r cubed by r cubed into, instead of the angular velocity I substitute the torque, okay, L I by 8 pi mu r cubed. Okay. And you can see once again that the r cubed cancels out to give me, this should be j here, okay, epsilon I j k L j x k by 8 pi mu times r cubed. Okay. Once again, the velocity disturbance due to the sphere when expressed in terms of the torque exerted on the sphere does not depend upon the radius of the sphere r. Okay. It depends only upon the torque as well as the position vector. So, even in the point particle limit, the velocity disturbance due to this, okay, is independent of the radius, okay, and therefore, you get a result for in the limit as r goes to 0, you get the torque due to the velocity disturbance due to a point dipole antisymmetric force moment, okay, and that has this form. It is directly proportional to the torque. Torque can be expressed as epsilon times the antisymmetric part of the rate of the force moment. Okay. So, therefore, the velocity disturbance due to the antisymmetric part, okay, gives me a velocity disturbance which decays as 1 over r square. Okay. So, we have a disturbance due to a force decreases as 1 over r, Oseen tensor times the force itself. The point force disturbance decreases as 1 over r. The next higher is the dipole moment. Okay. There is no net force exerted by the particle, but the force dotted with distance integrated over the surface is non-zero. So, there is a force dipole, can be of two types. One is due to a symmetric and the other is due to the antisymmetric. The disturbance due to the symmetric point force dipole goes as 1 over r square, is identical to the disturbance created by a sphere in an extensional symmetric traceless rate of deformation tensor far away. Antisymmetric part also decreases as 1 over r square. That disturbance is identical to what you get due to a rotating sphere, and of course, you can go to higher orders, but these are the basic types of disturbance that are there in the limit of low Reynolds number for a viscous flow. So, everything we have done so far is for external flows, flow around a particle. We took a sphere for simplicity, but even if the particle is more complicated, the slowest decaying part will be of this nature, okay, because ultimately when we got the result, okay, we found out that if we take only the slowest decaying term, it is not dependent upon the radius of the particle. It will not also depend upon the shape of the particle. It will depend only upon the force exerted by the particle. So, that so long as that force exerted by the particle is finite in the limit as the characteristic length goes to 0, you get the same value for the disturbance to the velocity field, both due to a net force as well as due to a force moment. Next, let us look at how we would solve for internal flows. The simplest example is, for example, a spherical drop, okay, with some external boundary conditions imposed on the surface of that drop. In this case, instead of taking the decaying harmonics, one would take the growing harmonics and solve the equations in exactly the same way. Okay. So, I will not go through that, I will just leave that as an exercise for you, but let us look at other types of internal flows. In particular, if the flow happens to be a two-dimensional internal flow, there are certain simplifications that one can make while solving the problem. Okay. So, let us look at two-dimensional. The simplest case one can consider is a Cartesian coordinate. Okay. A classic example of this is what is called the flow in a lid driven cavity, where you have 3 walls with velocity equal to 0 and you have one wall moving with a constant velocity, some constant velocity in the tangential direction. You cannot have motion normal to the wall, of course, because the fluid is incompressible. So, volume has to be conserved, but you can have a wall which is moving in the tangential direction. Okay. So, this is a two-dimensional flow, okay, where one has the coordinate system x and y. And the mass conservation equation for this case, okay, rather than using x and okay, we will work in x and y. Okay. Mass conservation equation partial u x by partial x plus partial u y by partial y is equal to 0. And we had discussed when we did kinematics that because the divergence of a vector is equal to 0, that vector can always be expressed as the curl of something. results in no major simplification in 3 dimensions, because we still have a vector whose curl we have to take. In 2 dimensions, there is a major simplification, because that vector is always perpendicular to the plane. Okay. The curl of the vector is in the plane, that vector itself is perpendicular to the plane. Okay. That vector perpendicular to the plane is E z, the unit vector, times the stream function psi. Okay. In particular, we can express in terms of the stream function u x is equal to partial psi by partial y, u y is equal to minus partial psi by partial x. You can see that written in this form, the equations identically satisfy the incompressibility condition. Okay. Now, this u x and u y in terms of the stream function can be substituted into the momentum conservation equations. Okay. So, the momentum conservation equations in the x and y directions are minus partial p by partial x plus del square u x is equal to 0, where del square is now in 2 dimensions, partial square by partial x square plus partial square by partial y square. Then you have minus partial p by partial y plus del square u y is equal to 0. Okay. Expressed in terms of the stream functions. Okay. So, I get minus partial p by partial x plus, I should put a viscosity here, sorry. There should be viscosity here in terms of both these terms, okay, with mu del square u x and mu del square u y. Okay. Okay. Minus partial p by partial y I can eliminate the pressure from these 2 equations just by the simple expedient of taking partial by partial y of the first equation, partial by partial x of the second equation, subtracting out. Okay. So, I take partial by partial y of the first equation, subtract out partial by partial x of the second equation. Therefore, the second derivative of p with respect to x and y cancels out, okay, and I will get an equation of the form mu partial square by partial y square, sorry, mu partial by partial y of del square partial psi by partial y plus mu partial by partial x of del square partial psi by partial x is equal to 0. Okay. So, that is the final equation I get for the stream function. Of course, I can interchange the order of differentiation, and if you do that, what you will get, as you can see quite easily, is that mu del square psi is equal to 0. Okay. Because since viscosity is not equal to 0, this is just gives me what is called the biharmonic equation for the stream function. Okay, the biharmonic is a 4th order equation. 2 Laplace operators acting on the stream function is equal to 0. Often this is also written as del power 4 psi is equal to 0. And the boundary conditions that you typically impose are u x is equal to partial psi by partial y, okay, and u y is equal to minus partial psi by partial x. So, boundary conditions for the derivative of psi with respect to both x and y are imposed on all boundaries, okay, and these have to be solved in order to get a solution. Okay. Of course, in Cartesian coordinates, the way to solve a Laplace equation we saw earlier when we did heat and mass transfer. You take partial x square plus partial y square of the temperatures equal to 0, identify the homogeneous boundary conditions, you get an eigenvalue problem in those 2 boundaries, and then the other 2 boundaries you get there is an inhomogeneous term, and the constants in that are determined from orthogonality relations for the eigenfunctions obtained in the eigenvalue problem. Okay. So, rather than solve for the full lid driven cavity, which is a little bit complicated, we will try to solve a simpler case. Okay. I will try to solve a simpler case here. That is, rather than solve for the entire lid driven cavity, we will focus on one particular corner of this lid driven cavity, where I have one wall which is stationary, the other wall which is moving tangentially, okay, and try to find out what is the velocity field there. So, the problem I will consider is, shall consider an infinite domain. This is the x axis, this is the y axis. This wall is moving with a constant velocity u. Okay, this wall is moving with a constant velocity u, and the velocity is equal to 0 on this wall. Okay. Because this wall is moving with a constant velocity u, I will end up having streamlines that look something like that. Okay. I would like to solve for those. Okay. Now, rather than solving this in a Cartesian coordinate system, it is simpler to solve it in a polar coordinate system. Okay. So, this is an r theta coordinate system, where the position vector to any distance, the distance from the origin, I will place my origin at the corner between these two boundaries. The distance from the origin is r, and this angle between the position vector and the x axis is theta. In this polar coordinate system, the mass conservation equation is 1 by r partial by partial r of r u r plus 1 by r partial u theta by partial theta is equal to 0. That is the mass conservation equation. This angle between the two plates, okay, I have shown it here as 90 degrees, but it does not have to be. Okay, it can be any angle. I will solve it for a general angle theta naught between the two plates. So, theta naught is the angle between the two plates, and theta is the angle made by the position vector from the x axis. So, that means that theta can go from 0 to theta naught. Okay. So, theta can go from 0 to theta naught. Okay. There is a stream function for the polar coordinate system as well. It is quite easy to obtain. Okay. U r is equal to 1 by r partial psi by partial theta. U theta is equal to minus partial psi by partial r. So, once again in terms of this, the equation, the biharmonic equation for the stream function becomes del square psi is equal to 0, where this operator del square in the polar coordinate system is 1 by r d by dr of r partial by partial r plus 1 by r square partial square by partial theta square. That is a Laplace operator in the polar coordinate system. You have to take 2 times, you have to operate 2 times in order to get the biharmonic operator. So, I have to solve this equation in order to obtain the stream function psi. Okay. What are the boundary conditions? Okay. Boundary conditions are on 2 axes. Okay. One is, let me take this y off here, because y and x are orthogonal axes, okay, whereas this angle theta naught could be any value. Okay. So, the boundary conditions are on the along one of the boundaries. Okay. Along one of the boundaries, the velocity has to be identically equal to 0. That means that both u r and u theta have to be equal to 0 along this boundary. Okay. That means that at theta is equal to 0, u r is equal to 0. That means that partial psi by partial theta is equal to 0 and u theta is equal to 0. That means that partial psi by partial r is not also equal to 0. Okay. So, that is the boundary condition at theta is equal to 0. At the other boundary, theta is equal to theta naught. Okay. The velocity is along the radial direction. Okay. It is tangential to the surface. The surface is along the radial direction. Therefore, the velocity is along the radial direction. That means that u r is non-zero. Okay. U theta is still 0 because there is no velocity perpendicular to this plane, okay, which is along the radial direction. So, u theta is equal to 0 means that partial psi by partial r is equal to 0 and u r is equal to capital U. That means that 1 by r partial psi by partial theta is equal to capital U. Okay. So, those are the boundary conditions. U r is equal to capital U, that means that 1 by r d psi by d theta is equal to capital U. U theta is equal to 0, that means that partial psi by partial r is equal to 0. Okay. How do we solve this? You can see from this boundary condition here, you can see from this boundary condition here, 1 by r partial psi by partial theta is equal to u, which is a constant. That means that I would expect psi to be proportional to r on the boundary. Okay. So, therefore, if I wanted to search for a similarity solution, I would look for a solution of the form psi is equal to r times some function of theta. Okay, because I expect on the boundary, I expect psi to be proportional to r, because partial psi by partial theta is equal to r times u. Therefore, I can search for a solution in which psi is equal to r times a function of theta everywhere. Okay. So, now in terms of the function f, what are the boundary conditions? Okay. The boundary conditions for f, okay, at theta is equal to 0, okay, partial psi by partial theta is equal to 0. Okay. Since partial psi by partial theta is equal to 0, I have df by d theta is equal to 0, okay, and partial psi by partial r. When I take the derivative of psi with respect to r, I just get f of theta. So, therefore, I have f of theta is equal to 0, okay, and at theta is equal to theta naught, okay, partial psi by partial r is still equal to 0, okay, because u theta is equal to 0. Therefore, partial psi by partial r is equal to 0, f of theta is equal to 0, and 1 by r partial psi by partial theta. 1 by r partial psi by partial theta is just df by d theta. This is equal to capital U. So, those are the boundary conditions for f. I substitute this form, okay, this form of the equation into this biharmonic equation, and then obtain a solution for obtain an equation for f of theta. Okay. So, let us do that a little quickly. Okay. So, del square psi is equal to 1 by r d by dr of r partial psi by partial r plus 1 by r square partial square psi by partial theta square. Okay. And if you work it out in terms of f, this works out to be equal to 1 over r into d square f by d theta square plus f. Okay. Just substitute for psi in terms of this in order to get this expression. Okay. I have to take another Laplacian. So, del square of del square psi, okay, is equal to, if you substitute once again, if you substitute this, okay, and take a second Laplacian, you will get 1 over r cubed into d power 4 f by d theta power 4 plus 2 d square f by d theta square plus f. This is equal to 0. Okay. So, therefore, my solution for f of theta is determined from the equation d 4 f by d theta power 4 plus 2 d square f by d theta square plus f is equal to 0. Linear differential equation can be solved quite easily. Okay. To get f is equal to a cos theta plus b sin theta plus c theta cos theta plus d theta sin theta, where a, b and c and d are the 4 constants of integration which have to be evaluated using the 4 boundary conditions that we have in here. Okay. These 4 constants of integration have to be evaluated using the 4 boundary conditions that we have in here. Okay. Just a little bit of algebra to do it. I will not go through the details, but I will just give you the final solution, that is f is equal to u into theta naught minus theta cos minus cos of theta naught plus theta minus 2 theta theta naught sin divided by 2 into theta naught square minus sin square theta naught. So, an analytical solution is possible for f, and the analytical solution for psi is just equal to r times f. Okay. It is equal to r times u times this complicated function of theta. Okay. So, this gives me the velocity fields. I can just take the derivatives of this. Okay. So, u r, okay, u r is equal to 1 by r partial psi by partial theta is equal to df by d theta, okay, and u theta is equal to minus partial psi by partial r is equal to f of theta. Okay. So, minus sign here. Okay. So, this gives me the final expression, okay, for the velocity fields. The next step is to actually calculate the force acting on the surface. For that, I need to calculate the shear stress, okay, to calculate the tangential force that is exerted on the surface. Okay. So, if for example, I want to find out what is the tangential force exerted on this surface, I need to calculate the stress. The stress in this case is tau r theta, okay. That is the force acting per unit area in the r direction. R direction is this direction, in the r direction, r is this direction, acting at a surface whose unit normal is in the theta direction. Okay. The force per unit area in the r direction acting at a surface whose unit normal is in the theta direction. Okay. So, this can be evaluated. Okay. The shear stress tau r theta, okay, turns out to be equal to mu into r by 2 d by dr of u theta by r plus 1 by 2 r partial u r by partial theta. Okay. Note that this shear stress is not straightforward. In a Cartesian coordinate system, tau x y will be equal to mu into partial u x by partial y plus partial u y by partial x. Okay. The symmetric traceless part of the rate of deformation tensor. In this case, you have to take into account that the unit vectors in this polar coordinate system also depend upon position. Okay. So, for this one has to go to standard tables in order to find out what is the expression for the shear stress in a curvilinear coordinate system, which incorporates the variation of the unit vectors with respect to position, and the final expression for that turns out to be equal to this one. Okay. And once again, this can be expressed in terms of the stream function and then ultimately in terms of the function f. Okay. It turns out this is equal to mu by 2 r into d square f d square f by d theta square plus f of theta. Okay. So, this is the expression for the stress anywhere within the flow. Okay. In particular, the stress on the wall, okay, that is tau r theta at theta is equal to theta naught. Okay. one can get an analytical expression for that. Okay. It turns out to be equal to mu by 2 r into 2 theta naught minus sine by theta naught square minus sine square theta naught. So, this is the expression that you get for the stress. An important point I would like to bring to your notice at this stage. The stress in this flow actually decreases as is proportional to 1 over r. Okay. So, in other words, as r goes to 0, the stress goes to infinity. Okay. R going to 0 means that I am coming towards the corner here. Okay. R going to 0 means that I am coming towards the corner here. Okay. I am coming towards the corner, R going to 0, because my origin is at the corner between the two plates. One plate is moving, the other plate is stationary. That means that the velocity is discontinuous at this corner between the two plates. And as r goes to 0, because of this velocity discontinuity, the stress actually goes to infinity proportional to 1 over r. Okay. This is a standard feature of all corner flows, okay, an important one for these kinds of lead driven cavity flows. As you go towards the corner, the stress increases as 1 over r as r goes to 0. Okay. The force per unit area, okay, stress is a force per unit area. So, to find the total force on this plate, I have to integrate the stress over the radial coordinate. Okay. To get the total force on the plate, I have to integrate the stress over the radial coordinate. Integrate the stress, stress is proportional to 1 over r, that means the force is proportional to log of r. So, the force exerted is actually infinite. It diverges proportional to log of r in the limit as r when there is a discontinuity in the velocity at the corner between these two plates. And this is an important issue in all such problems which involve flows in which there is a discontinuity in the velocity at a corner. Okay. Of course, there is no resolution to this. The Stokes flow equations do predict in fact that there is a discontinuity, and that is a disadvantage of Stokes flow solutions. This paradox can be resolved only if we do away with the continuum approximation. Okay. This assumes that in the limit as r goes to 0, the flow is still in the continuum regime. However, as you go closer and closer, at some point the distance from the corner is going to become comparable to the mean free path. At that point, the continuum approximation will break down, okay, and because of that you will get a finite result. However, if you take the continuum approximation all the way to r is equal to 0, you do get the result that there is a singularity in the net force, there is a singularity in the stress as well for all these kinds of internal flows. Okay. So, this just gives you one part of the solution, okay, for this particular case where I have focused attention on one particular corner within the flow where there is a discontinuity in the velocity at the corner. One could solve the entire problem in a similar manner in using a Cartesian coordinate system. Okay. We will not go through that, it is a little complicated mathematically, okay, but just to bring to your notice that one can solve these kinds of problems in 2 dimensions by using a simplified stream function formulation where we write the velocity field in terms of the stream function. This is always possible in 2 dimensions. Once you have done that, you get a biharmonic equation, and that biharmonic equation can be solved subject to boundary conditions in order to obtain the Stokes flow solution.